So we have a cylinder with a piston inside it. We want to find the relationship between pressure and volume. Here the volume is high, the pressure is low. When this thing goes down, the volume is going to be low and the pressure is going to be high. So there's going to be an inverse relationship. We start with the first law of thermodynamics. We assume there's no heat going in or out of the piston. That is the adiabatic assumption. And we're going to take this term and move work over to the left-hand side. Okay, so intuitively we know that, or not intuitively, empirically we know that change in internal energy is the number of moles times the specific gas constant volume, times the change in temperature. And we know that work is equal to pressure times the change in volume. Well, we're going to use the ideal gas law. PV equals nRT. We're going to divide both sides by V. And instead of writing PdV for work, we're going to write nRT over V dV. That is equal to work. First thing you'll notice, this should be an N. N is the common factor, so we can cancel out. Divide both sides by RT, and we have the new equation, C sub V over R dt over T plus dV over V equal to 0. So this is set up where you can integrate both sides because you have that differential term. So we integrate that, and our from T1 to T2 and from V1 to V2. Our denominator is the variable. Our variable is in the denominator, and it's to the first power, so that's the natural log. And it's going to be the natural log of T2 minus the natural log of T1, but we can rewrite it as the coefficient. We can combine the arguments, and instead of having a minus sign, we get a division inside the argument. This is multiplied by C sub V over R. And it's the same thing here. V2 over V1. All right, this can be the exponent of the argument. And we can combine the logs. Again, using the same thing we did earlier. Now we're multiplying. We're combining the arguments and multiplying instead of adding. And this is all raised to the C sub V over R. This is equal to 0. So, interesting thing about the log function, any log function, but the natural log as well, it's going to pass to this point 1, 0. And so we know that if the natural log of anything is equal to 0, then the argument here has to be equal to 1. So we get rid of the natural log. And we just have T2 over T1. So the C sub V over R multiplied by V2 over V1. equal to 1, because we know the argument here, the x value, is 1 if the y value is 0 for any log function. All right, and this one is pretty easy from here on out. We raise both sides to the r over c sub v. T2 over T1 times V2 over V1 to the R over C sub V equals to 1. And what we want is pressure and volume instead of temperature and volume. And so we're going to go ahead and use PV equals nRT again, except we're going to write T equals PV over NR. And right, so NR, common factor, doesn't matter. We are at a new equation, PV2, V2, R over C sub V over P1, V1, V1, R over C sub V equals 1. And so you can combine this, the exponent, since the bases are the same, you can put this V1 and this V2 up into the exponents, and that will be 1 plus R over C sub V, or we put a common factor. C sub V plus R over C sub V and since this is equal to 1, you can rewrite this as P1 V1 C sub V plus R over C sub V equals P2 V2 C sub V plus R over C sub V. These are both in the exponent. I didn't draw it very well. So what this means is that P1, or this value equals this value at all times. And so that will mean that the product of P and V plus R is equal to a constant. If A times B always equals 10, if A1 times B1 plus A2 times if A1
times B1 equals A2 times B2, then A1 times A times B is equal to a constant. That's what I was trying to say. And so we just derived pressure and volume, this relationship. We also have the temperature and volume relationship, and that's useful if you're trying to like design a Stirling engine and figure out what's happening to the heat in here. But that's the derivation. Thanks for watching. If you hate this video, give it a thumbs down.